Okay, so last time we introduced this composite pattern. Let's just remember what a motivating problem is. Of course, the problem you have to solve later, not just for this course, but once you go into job, may not be as specific as this. But here's the principle. Every time, if you see for your particular application you want to build, if you got basic components versus recursive components, eventually your system will just be like a tree for which you can recursively traverse, like what you learned in 2011. Then it's a composite pattern. It's a very good candidate for that design pattern. Okay, that's just want to remind you. Okay, so now what we end up having last time was to give you solution, right? And okay, we talked about multiple inheritance for sure. And this was our first design attempt. I'll go over this slide in the last, okay? Just about the summary of the pattern that we're going to learn. I want you to consider this diagram very quickly, okay? So that's our first design attempt, where we simply put the children, okay, I wouldn't go to iPad, just remind you very quickly. You can refer to the lecture from last time if you wish. You can see that from this first design, the children feature over here, which is a list of equipments. That one there simply belongs to equipments, which means even the basic components like a disk drive and video card have children. That one might work programmatically, but doesn't make any reality sense. Because in reality, you wouldn't have a video card that has one child of type disk drive, right? That wouldn't make sense. Okay? That's how you argue that the first design attempt is not the way to go. Because you can have some very unrealistic scenario happening in your system. Any question about this design? Okay? Okay. And then what we did was to introduce to you the composite pattern. Let's have a look. Okay? So this is pretty much where we end up having. Okay? So that's the composite pattern here. Let's just go over the architecture very quickly. And then we have to consider a very important question, and to make it even more general, to put it in perspective. Okay, so now if you look at that, we have still the equipment class at the top, and also we got a price feature. Okay? So every equipment has a price. Doesn't matter that's the disk drive or cabinets. Doesn't matter. Okay, every equipment has a price. And then you can see that we have a separate class over here called composite over here, where we, for separation of concern, we only put features that's related to the tree structure in the composite class. For example, we got children. Also, we got add child. Later on, for your project, for example, you may want to consider, rather than having list over here, you can have iterable, so that you can practice more about the iterable pattern. Okay? And you can see over here for composite equipments, you can see it has two parents. It has equipments over here. Also, it has composite. So that's multiple inheritance, right? And for every basic equipment over here, it has only one single parent class, which is equipments. Which means for this drive, the idea about composite is not applicable. Okay? That's kind of the details you want to pay attention to. One more thing to say. You can see in the case of one small detail. You can see when we talk about composite over here, we have generic parameter t, which means t may be instantiated by anything, right? Generally. But now, when we actually inherit this particular composite equipment, can you imagine how you would declare this composite equipment programmatically? Okay, I will help you out to start with. That's really important to pay attention to this detail. What I would say is, for this particular one, I would say class composite equipment. Okay, I'll just for short, composite equipments inherits, and then I would say composite over here. Okay, I'll say comp. So now, what should we instantiate over here? You basically got two options. Option number one, you can simply say the composite equipment class itself also takes a generic parameter. And then you will simply say the t, whatever t I instantiate that into, is going to be applied over here. That's option number one. Okay? Option number two, I'll write it down. So this is option number one. And for option number two, I would say class composite equipments And then I don't make it generic. I don't. Because I can commit to say every element in the tree should be of type equipments. Okay? How do I do that? I can say inherits over here, composite, and then I can put a concrete class over here, equipments. Okay, again, we have a design decision to make. I'm proposing two possible designs to you. Should one or two be adopted? Well, if you believe one should not be adopted, you should tell me why. Or you think both are acceptable. You think two should be adopted, for example, okay? So why would you think one is not good?
Because like you said, for the last one, if we have also like a composite furniture, we're looking at composite equipment with furniture objects.
Exactly. Think about what one will lead to, right? You really want to think about this kind of issue here. Let's say, hypothetically, I chose number one. Let's say, I'll use pink. Let's say I choose number one. Let's see how problematic it might be. If I simply chose one, and now let's say I get to the cabinet class over here, right? What about for cabinets? For cabinets, I can easily say class, cabinets, and since we will talk about equipments hierarchy, right? So cabinets should only hold equipments only, right? It shouldn't hold any furniture, for example. But now, if I go to class cabinets, I can say inherits, let's say composite equipments, and then I can say something here, furniture. So now, does this particular use case make sense for our example? No, it doesn't, because now we talk about computer equipments, but now you're talking about cabinets which might store furniture, chair, right? You're basically mixing up the concept. So the very root of the problem is you want to be able to make an educational judgment over here to say either I want to go for option number one or go for option number two. The way we judge for that is to say if you actually went for option number one, you can have this particular scenario where you simply say every cabinet is going to hold some furniture, for example, chair. It doesn't make sense for this particular application, okay? And that could well be an exam question, right? I simply gave you this diagram here. I said, consider this particular composite class. I got either one or two to be chosen. Which one should you choose, right? You want to be able to judge. Question.
Could you give a use case of an example where the first option would be a good use case? Like, for example, let's say, like, for example, we had a composite, right?
Yeah. For this particular example over here, no, I'm not talking about a composite. I'm talking about a composite equipments. So over here, if you think about for this particular class, if you're down to this particular level, right, you're talking about composite equipments is substitutable for any equipments. So now we are talking about, there should be no ambiguity. We are talking about equipments only. It cannot leave any room for furniture. So for composite equipments, you should not go for number one, because number one will let you actually have furniture eventually. That's not good, okay, for this one here. So, but for this guy here, up, you can make it generic. That's not a problem, as we'll see later. Guys, any questions? There's something we didn't talk about last time, just new addition, right? So that's kind of the design issue you want to get straight, okay? And also be able to express your ideas in the exam or in the written test. Any questions? Okay. And the question that we proposed last time was about why is this particular composite class a separate class, as opposed to having these two features over here, the children and add child. Alternatively, we could have put them in here, in the composite equipments, right? That's what we said last time, right? So now, anybody want to try? We explained that already before I present to you a prettier diagram. Anybody want to explain why it would be a better design if the composite class is a separate class from the rest of the equipment cluster? Yes?
The single choice principle, if we have other classes that also make use of composite features, then you want to also have like one superclass.
Yes, exactly true. Okay, it's something to do with single choice principle. I'll explain that in just a moment. But the short answer to this is single choice principle. Okay, single choice principle. Let's see how it can be discussed. Okay, so now let's talk about a different diagram. However, I want you to pay attention to the following details. Okay. Okay. Is the font size okay? Is it readable from the back? Okay, somehow readable? Okay, you can also download the diagram from the website. Okay, it's also on the lecture's website. So what you can see is, first of all, at the top level there, we got composite. And then where we got children, and we got add child. And the composite is generic of type G. Okay, it's completely general, not specific to any cluster. And then we got one cluster over here. We got one cluster over there. So we got two instantiations of the same pattern, composite. Okay? You can think about, on the one hand, so this is one instantiation of the composite pattern. On the other hand, another cluster which is totally independent. So this is just another instantiation. And if you look at the structure of the classes over there, you can see we got the general equipments versus the general furniture. And we got base equipments like a disk drive and also video card. Also, we got the base furniture like a desk and chair. Right? We got base versus recursive. Let's say recursive. We got composite equipments versus composite furniture. Right? So now you can imagine that the following. Let me reinforce what I just said. How would this particular class be defined? I'm going to say class composite equipments. And then I can say inherits over here. And then I can say composite here. I'll say composite. And then I'll put somebody over here. Okay, I'll leave that just for now. Versus, for this particular composite furniture, when I define that, let's say, at the Eiffel level, composite furniture. And then I say inherits over here. And then I can say composite, right? I'm referring to the same general class. And then put something over here. What's left unspecified? Will they be the same class or different? Different, right? Okay, hopefully you can now see. Okay. Well, I'm pretty sure you can work it out, but I'll just tell you what they should be. For this guy here, you will just refer to any equipments, because now we're in this particular cluster. So that will just be equipments. And then for this guy here, you can be any furniture. And why is that obeying the single choice principle? It's because now all the code about children and add child that's defined in the composite class will be reused among different clusters. And each cluster simply represents different independent instantiation of the composite design pattern. Okay, okay, that's more extension to what we said from last time. Okay, guys, any questions? You okay? Okay, good. Now let's move on to how we can write some code about the composite pattern. Okay, let's go over some code. Okay. Yeah, so rather than going over the slides with you, so I'll just show you directly every class you should really pay attention to. Okay, I want you to look at the code here. Okay, I'm going to go over class by class with you. But now notice that we got 1, 2, 3, 4, 4 classes to worry about, right? And also we got multiple inheritance. If you look at the blue box, the deep blue on the right-hand side, you can see that one there has two parent classes. One is equipments, the other one is composite, right? Okay, notice that. Okay, let's go over some implementation details, and then we have to write some application code and trace it and see how things might happen. Okay. Remember, our goal eventually is to say, when we got a diagram like this, eventually, okay, I'll just remind you very quickly. Eventually, when we build up a system like this, we want to say, I want to go to the top level cabinets and ask what's the aggregated price for everything that's contained in the cabinets. That's what we like to calculate. But we're going to see how to do that at the runtime. We'll get there. Okay. Before I do that, I just want to go over some code with you. Okay, so the code over here, oh, how about we just go over this, and then I can highlight an iPad. That might be a better idea. First of all, we have the composite class, which is completely generic. You can replace T by anything. It can be G, can be E. Okay, it's up to you. And then we got children, just put linked list. You can make it iterable if you wish. And also we got to add child of type T. Okay, children that extend. So this is only going to be defined in one place and reused among clusters. Okay, so here I say polymorphism. Okay, so that means, let's say for example, if I, in the equipment cluster, if I instantiate the composite over here by equipments. So what I meant was, if you go back here, you can see for this particular one, I simply instantiate that by equipments. So that means for this particular one, that's green. Okay, I'll say green here. So that means for the children over here, okay, I'll make it bigger. So that means G is going to be replaced by equipments. That's one instantiation. And also, and whenever we want to add child, it's also going to be equipments. And remember, back in the inheritance lecture, if you have the feature parameter be equipments, what can you pass in order to add it? Any of the descendant classes of equipments, right? Just remember that. So that's where polymorphism can occur. And given that the equipment is now the static type for the parameter, at the run, what can you add to it? Basically, what are the descendant classes of equipments? It can be this drive, it can be video card, it can also be any of the composite equipments, right? Including all the descendants here. Okay, that's where polymorphism is very powerful. Questions? Okay, yeah, we just try to build, we try to review what you have seen before and apply that to the design patterns. Okay, after this, I'll come back here. Okay, you can do some exercise, maybe for your projects, which will be released at some point soon. The second class we can look at would be the composite equipments. The composite equipment is basically, okay, we just talked about the composite class over here. This is what we just talked about, right? So now we talk about composite equipments, okay? So we say composite equipment inherits equipments and also inherit composite, which will instantiate the T by equipments, right? And then we got the make, etc., right? So you can simply create some empty children to begin with. And also we got a price. So now let's say in the composite equipment class, we are simply just going to make the following loop. Let's say we want to make it a query. Let me show you the code right away. You want to take a guess? Let's say this. If the composite equipment we're talking about is cabinets, let's say, and the cabinets might contain multiple disk drive, for example, well, the cabinets might contain several mini cabinets, right? It's recursive. How can we define this particular price query for composite equipments, given what we have so far? Anybody, any idea? Should you simply say result is assigned to $100? Is it always going to be the fixed price? Well, intuitively, the more components you contain, the cabinets, the more it should be worth, right? So it shouldn't be a fixed number.
So do you check to see if it's like a composite piece of equipment? If it's not, do you just return the price? And if it is, do you run it recursively on its children?
Somehow you have to run recursively, yes. So now, how would you suggest to write a code? That's the question. We talk about polymorphic collection, basically, right? We talk about polymorphism, yes.
It's a cabinet that will, other cabinets, then the base case is like going to use something like a disk drive.
Uh-huh.
And then the recursive case is if there's like a cabinet.
Okay, yeah, you got base case, you got recursive cases. But do you have to say over here to say if the current class is actually the base like a disk drive, or it is like maybe a video card, then you return the price. Otherwise, you try to do recursively. That might be a little bit too over-complicated. Let me show you what you should write easily. Remember, it inherits from the composite class. And the composite class, we got children, remember? And every child is simply equipments. That's what we have instantiated into. So what you can say is this loop. I could have used across is, but I just say across s. Okay? Across the children as cursor. Question for you. When I say over there cursor.item, okay, I'll switch to the iPad and ask you that question more precisely. Okay, have a look at that. You know what? I'll make these two classes. Okay, look at the pink class and the deep blue class. I want to ask you about this line particularly. Cursor.item. question is simple. What is the static type? Equipments or composite equipments? How do you tell it's equipments? It's whatever inherits, right? Instantiate into. Okay, just make sure. I want to make sure. Good, good, good. Because when we instantiate this particular guy to be equipments, that means every occurrence of T has been replaced by equipments. And also this guy here is simply equipments. So when you say children over here, across the children, every item there is of type equipments statically. Okay, just make sure. Good. Now, this is everything you gotta write. You can see it doesn't seem to be a recursive call, does it? In some way, it doesn't seem like. Because if you want to make a recursive call, what you would have done would be to say, this is a price. I would have said something like, I just call price directly. But now I'm not doing that. I simply say, whatever cursor the item is, I call price on that. It doesn't seem like the recursion that you learned in 2030. Do you get that point? However, it turns out when you execute this particular loop in the runtime, it's almost like a recursion. Because after all, the tree you're trying to traverse is recursive. If I claim that this particular loop, which doesn't look like recursion, will work, it will run just like a recursion. Okay? But we're going to see exactly how to execute this. Okay. So now, after this, I want to go over two more classes. Okay, so now you can see also we got the equipments class where we got name and we got a price. Okay, and also we got the basic components, for example, video card. In which case, we can simply set its price to be some fixed value. That is okay. For the leaves of the tree, those are the base cases. You can set some fixed price to them. But for composite equipments, you can see that in this case, the price cannot be attributes. It cannot be a fixed price. It has to somehow add up all the contained components in it. Right? Okay. In case you're a little bit lost, what I have just explained was consider the price over here and the price over here. From the client's point of view, they will simply say video card, the price. Or they would say cabinets, the price. From the client's point of view, it's the same. However, what's going to be calculated will be different. In the case of the basic components on the left-hand side, you will simply return the value right away. Right? That's the base case. On the right-hand side, it's actually going to go over each of its children and do something on that. Okay? Let's see exactly how that's going to work. Okay? Guys, are you okay so far? Okay. So now let's see this. We have to look at some code in order to tell. Okay, let's go over some code together. Let's go over the overall very quickly, and I'll trace it together with you. Let's say we got two equipments here, cart and drive. They're both basic. Also, we got cabinets, which is our cabinets, right? And remember, cabinet is a composite, right? Remember. And then we got chassis. That's also composite. And also we got bus. Basically, cabinets, chassis, and bus, they're all composite. They are like internal nodes of your tree. And let's say we create some carts, we create some disk drive. Also, we say we create some bus. Also create some chassis. And also create some cabinets. Okay, so far we have created 5 different objects. They have no connection to each other just yet. So now, you can think about we create a node separately first, and then we try to connect the nodes in order to form a tree. That's what we will do. Let's see how we can do it. First of all, you say the bus.add cart. Okay? That means car becomes one of its children. And then we say chassis.add bus. And then, etc. Okay? We just build a tree. So now, finally, what we have to trace is to see after building this particular tree, what's going to happen if we say cabinets, which is the top level component of the tree, the root. If we say cabinets are price, what's going to happen? Right? That's something you're supposed to know. Okay? Let's trace it quickly. Okay, so what I will do is I'll go back here. Okay? Let's see what's going to happen here. So I got some diagram over there. So this, you can see for this particular diagram, let's see what we have so far. Okay? So we have, first of all, we got cart, which correspond to, let me just do it again. We got cart here, which correspond to this particular cart objects. We got disk drive, which correspond to this particular disk drive. We got bus, which correspond to this bus here. And also we got two chassis, which correspond to these two chassis. Oh, sorry. One chassis over here, and also one cabinet, which is here. Right? That's the nodes we have created. You can see it's almost like a tree, almost, except that nothing has been connecting between the nodes. And we're going to do that. Okay? Okay, let's do that quickly. So now if I say bus.add cart, so bus is talking about this particular bus objects, and then we say .add cart. Cart is this particular object here. So when we say added, so that means now the first child of bus is now going to point to this particular cart, right? Okay, good. And then we're going to do, let's say chassis.bus, sorry, chassis.add bus, and chassis.add drive. How do we do that? So chassis is over here, and then we're going to add two things over here. So we're going to add a bus over here, right? That's a bus. And then we're going to add the drive. That's a drive. Two children. Okay? Let me improve that just a little bit. It doesn't look like an arrow, does it? Okay, finally, let's do the pink over here. When we say cabinets.add chassis, that means for the cabinets over here has only one child after this. So the first child is going to point to chassis. That's how we build a tree. Well, that's pretty nice. We got 1, 2, 3, 4. We got 4 levels of tree already. Okay? Guys, any questions so far? Any questions? Okay, so now let's see how we can trace this particular line. Let's see that. What I want to trace is this particular guy here, cabinets.price. You can think about cabinets over here is referring to the top level or the root of the tree. Okay? If I say cabinets.price, what's going to happen? Okay? Let's see this. You got two versions of the price. You got one version over here of the price, which belongs to the composite equipments. You got another version over here of the price, which belongs to the equipments. When I say cabinets.price, am I going to call version number 1 or version number 2? I heard 2. Is that because of static typing or dynamic binding? Dynamic binding, right? If I talk about runtime, which version? Okay, just make sure. Okay? So now when we say cabinet.price, because of dynamic binding, we're going to call according to this type over here. So what we will do is we're going to execute this particular loop. How many iterations are we going to have? 1 or 2? Be sure. 1, because there's only one child over here, right? So now when we say cursor.item over here is basically going to refer to the first child, which is chassis. I'll put it here. Okay? Okay? So now when we say, I'm going to change color here. When I say chassis.price, which version am I going to call? 1 or 2? 2, right? Because chassis over here that I'm referring to has the dynamic type chassis. And now, that means chassis.price is going to execute also this block of code again. So now, how many iterations do I have? 2, right? Okay, can you get an idea? Let's do that quickly, okay? So now, 2 iterations. So now, for the first iteration, what we will get is, we're going to refer to the first child, which is referring to this particular bus, right? So now, for that one there, we're going to say bus.price. What's bus.price? Which version are we going to call? 1 or 2? Bus is over here, right? Remember, bus is composite, right? So that means for bus, we're also going to call this version again, okay? Remember the dynamic type bus, okay? How many iterations? 1, very good. So what we'll do is 1 iteration is referring to the car, okay? Again, it's referring to the cart. So that means cart at the last time. We're going to say cart dot price. Are we now ready to reach the base case? When you say cart.price, dynamic type is equipments. So the closest one you can call would be not this guy here. It doesn't belong to composite equipments. It belongs to equipments. In that case, you will call this particular price over here, whatever that has been set up. Remember, for the cart, its price has been set up to 200, right? So now that means cart.price is going to give to you 200. Okay, that's one side, all right? So that means for the plus over here, it's going to be plus 200 for the first time, okay? And now we are done with this particular bus over here. So for the bus, there's only one iteration to go. So now we're going to continue with this particular chassis that children, right? We're going to continue with that, okay? And then continue with that. So now, if you go to the second iteration, let's see this. If you go for the second iteration, it's now going to point to this particular drive. So what you will do is you're going to say drive.price. Now, version 1 or version 2, 1, right? Because drive, again, is a basic components. So now drive is over here. Sorry, circle the wrong thing. Over here, it's been set to 500. So that'll be 500. Okay, eventually when you add them up, you're going to have 500 over here and 200 over here. When you add them up together, eventually we'll just get 700. Okay, for the rest of the time, the tracing, it will be like a normal recursion when you return. Any idea? Any questions? Questions first, and I'll come to you. Yes. In some way, no. Actually, this you go for the root, and then if you think about the traversal, I see what you want to say. Okay. Let's try to highlight that. Okay. First of all, it's not a binary tree. Agree? May not be a binary tree. Let's say we got top level equipments over here, and somehow you might have several children over here. It's more like a B tree, right? And then over here, you also have maybe 1, 2, and 3. This guy here, you got 1, and here you got 1 and 2. What's the order of traversing it, right? So let's think about it. I'm glad you asked that question. That's good. We start from here, and then before we know the aggregate price for this, we have to know what's the price for this guy here. Before we can know for that, we should know its child, this guy here, and this guy here. So this is the first time we try to return. Okay? After that, we're going to figure out exactly what's the price for the second child. Right? In order to do that, we want to figure out every child of that. In that case, we're going to go for each child. That's the only child. And that one return. Okay? Similarly, we're also going to figure out what's the price for the third child. In that case, you got 1 and 2 sub-children. And then once you add them up, you're going to return. So now after that, what you will have is you're going to get one answer here, one answer here, and one answer here. Finally, you can return that. So it's not exactly, I would say, yeah, if you say pre-order, I would say that's okay. That's okay. Yeah, you always go for the parents. Before you can figure out the answer for the parents, you're going to figure out all the answer for the children. Yes, pre-order is fine. Yes. Guys, are you convinced it's pre-order traversal in some way? Yeah. Just in case you could not be convinced, I just try to show you. Right? Of course, one thing to note before I answer your question. The composite pattern itself is very general. It simply gives you a tree structure. This particular price feature has done using a pre-order traversal. It doesn't mean for every other feature you want to support, you have to use pre-order all the time. You may use post-order, you might use in order. Okay. I would say for this particular, yeah, I would say it might be difficult over here. Because when you call the price, you're talking about calling the price on your parents. In order to figure that out, you have to figure out the price for every children. Naturally, just pre-order. Naturally, yeah. Yes, question?
Professor, I have 2 questions. First, what would you consider this example in terms of hardness, 1, and 2, would you recommend always having a recursive strategy in terms of thinking about...
What do you mean the hardness of this example? You mean...
How, like, if
Uh-huh.
Where would you scale this particular example, like in terms of
I would say this question is pretty basic because we got a composite pattern over here, and then somehow you want to build a tree out of your composite structure, right? I would say that's quite basic. I wouldn't think that's difficult. Of course, if you got trouble of that, you may have some gap between 2011 and 3311. The best way to do, talk to me in the office hour, right? Yeah. And then how can this be asked in exam? I would say, for number one, ask you to come up with architecture for the composite pattern for the particular example I give to you. Number two, once you got your design, I want you to write a fragment of code which will illustrate how the tree can be built recursively. Number three, you're going to show me how you can do a traversal on the tree. But I will actually, I'll leave the last question a little bit later because we're going to see another pattern to see how we can do traversal of the tree more systematically, more elegantly, I should say.
So what if the composite object itself had a price? So the composite objects are just made up of you know how there's two ways to define the feature price?
Yes.
What if the composite object itself had a price? Like the composite object name was $500.
Mm-hmm. Oh yeah, sure. Yeah, you're basically talking about some extra computation, right? So for example, you might have something like this. You might have, I'll just mention that very quickly. For example, let's say this. Let's say for every composite equipment over here, you may define just another attribute, for example. You might say something that's extra, for example, right? Let's say extra. And then that one can be of type real. And then for every kinds of composite, you can simply set this extra to be different. Maybe the extra for cabinets is different from the extra for chassis, right? And then all you got to do is to say, when I try to calculate this particular line over here, every time once I get my price for every children, I can say after the loop, I can say result is assigned to result plus extra. Maybe that's what you're asking, I believe, right? Yeah, definitely. You know, well, we only talk about some basic principle, you know, with some extension, but you can be as creative as you might find necessary. Yeah. All right. Any questions from this side? Okay, to make sure I'm fair. Okay, so that's about the tracing of the code. Let's see anything else. Okay, I want to say one more thing about composite pattern, and then we can go to the more interesting extension, visitor. We'll get there. What I want to do is I want to go to this particular guy over here about the summary. Oops. Let me just move that away. Okay. If you try to, so this will be the slide you look at when you study the composite pattern, now that you have some idea. The design will be, we want to categorize the artifacts for this particular example into base versus recursive, or base versus composite. And then we got programming. How do we do that programmatically? We say that we got tree structure, you know, build a hierarchy using inheritance. Statically, we got inheritance. Dynamically, we got tree. Okay. At the runtime, that's where polymorphism and dynamic binding will come into play, right? So we say that, okay, so this sentence is here important. What do I mean by uniformly? You can think about the price feature was declared over here in the equipment class, which means every client who is using this particular, you can think about some client C who's using the equipment class, they can always refer to just the price. But the price might mean different things. It might simply mean the price at the basic equipment level. Or it might mean the price that's at the composite equipment level, right? There are two different versions of the price, depending on what the dynamic type is. Okay, number one. And polymorphism, right? Once you define the static type for the node of the tree to be equipments, dynamically it can be any descendant classes of equipments. And then dynamic binding, right? In this case, if I say, for example, let's say E is of type equipments. Dynamically, what can be the dynamic type for E? Any descendant classes of equipments, right? So now if I say E the price, now if I only say E the price, can you tell me right away which version of the price is going to be called? Oh, you know what? Only E the price. Forget about this drive. If I only tell you E the price, okay, let me make myself very clear. Okay, in case you got any confusion. This is really important. I'm asking the following question. Let's say I declare E of type equipments. Dot, dot, dot. E dot price. The question is, which version of the price is going to be called? Is it the version from equipments, or is it the version from composite equipments? What if E dynamically is pointing to a cabinet objects? Yeah, so it could be equipments, or it could be composite equipment. So which one? Which one? Make a choice. Dynamic type, yes, exactly. So your answer should be, it depends. Yeah, that's a valid answer, right? It's a valid answer. It depends. If I simply put a fragment of this in the exam, I ask you at this particular line here, I'm simply asking which version of price will be called. Okay, that's my question. Your question, if you simply say, it's going to call the first version from the equipments, wrong answer. If you say it's going to call the version from the composite equipments, wrong answer. Okay, here's the correct answer. I'll write it down. The correct answer should be, it depends on what dot 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 does to change E's dynamic type. So here, dynamic type is really important. Maybe somehow after executing this part of the code, E is now pointing to some video card. In that case, you should call the first version from the equipments, right? Alternatively, if this side of the code is going to be such that it's going to modify E such that it's going to point to some cabinets objects, in that case, you will call the second version from the composite equipments, right? So it really depends. Question?
Professor, if we have a polymorphic array
Yeah.
where the static type, for example, is equipment.
Sure.
In any polymorphic array, are we always limited to, because the descendant classes could have different features?
Yes, exactly. Yeah. Yeah. Again, you're basically you're going back to our design. I'll mention again. It's really important. So the question, I'll rephrase it a little bit. Okay. Let's make sure. Okay. So this one here. I hope everybody is okay. Okay. This one here. Let's make E a composite type. I mean collection type. Let's say this. If I say E is of type, let's ES equipments. Okay. Array of equipments. Okay, and I do dot dot dot. Okay, now question number one for you. Can I say ES at position 2, the second equipment? Let's assume there's such an equipment. Let's assume. Okay, dot price. Okay, I'll get to your question just in a moment. Okay, question number one. Compile. Yes, okay. Because static type for every element, including at position 2, is equipments. Equipments does define price, okay? Question 2, which version of price? Aha, you learn pretty soon, pretty quickly, that's good. Which version? Depends. Okay, if you're wondering about the answer, refer to the previous one, okay? Now, let me get to your points. Let's say I got another line of code over here. If I say ES at position 2 dot add child, and then let's assume I have VC being a video card, let's say, okay? And at the same time, let me assume the following scenario. Let's say for this particular ES, okay, ES is now pointing to an array over here, right? Let's say it got many different elements, okay, so on. Let's say the first element is pointing to a video card, let's say VC. It's a basic equipment. And it's polymorphic, so let's say the second element over here is pointing to a, let's say, cabinets. Okay, so now I want you to get focused on these two. Given that the dynamic type of the second element over here is cabinets, can I say ES at position 2 dot add child VC? Can I or can I not? Did you realize I deliberately try to mislead you? Let me mislead you again. Okay. Okay, let me say my question again. It's really important, right? Given that I have a polymorphic array of equipments, dynamically, position 2 is pointing to a cabinets object, which is composite. Now, can I or can I not say ES at position 2, which is referring to this particular cabinet objects? Can I say that.addChild? I heard yes. Just yes or no, according to the setup. For those of you who said yes, okay, you got to review the inheritance lecture. I'm here serious. Okay, otherwise you're going to have some trouble in the exam. Okay, the answer is no, because as far as compilation is concerned, what do we consider? Only static type. Exactly right. Okay, if you look at that, ES at position 2 doesn't matter what the dynamic type is. Doesn't matter. Ignore that for now. Equipments. Okay, static type is equipments. Does equipment support addChild? No. Okay, doesn't compile. Now, follow-up question. If I'm so sure it's really pointing to a cabinets, what should I do? Cast, exactly. Now, and back to your really original question. If you find yourself so often you have to do a cast like this to cast your elements of the array being statically equipments into, let's say cabinets so often. That means the original design decision may be wrong. Okay, guys, I hope that helps, to reinforce the idea. It takes a little bit longer, but I think it's worth it. Okay, good. Any question about composite before we say goodbye to it? Yes?
So I'm just reading scenario there. So you could just avoid that scenario by having the right design choice. So in that sense, like very on the exam. Like,
Oh, in the exam, it can be anything, right? I might give you a design decision that's totally correct, and then I might mislead you in a way that sounds like it's wrong. And then you got to justify, right? But it can be anything. So in the exam, you want to be so sure about whatever you have really understood is the right knowledge and apply that, right? And the way I ask the question, you shouldn't be misled by me, right?
So then how would you fix this? How would you fix it?
How would you fix, you mean this one here?
The one where you just misled it. Like, okay, so
Oh, okay, oh.
ask very often. How would you
Oh, yeah, exactly. So Michael's question was, let's say you find yourself so often that most of the elements you store in this particular array just happen to be cabinets. Maybe it should be just a cabinet array as opposed to equipment array. In that case, what you should have modified is to really say, rather than having static typing equipments, maybe that should be cabinets, or composite at least, right? That's how you fix it. Yes, good. Yeah, do apply this kind of knowledge. You learn the knowledge not just for the exam, for your future job, right? Or your future usage. Right? Just make sure you understand that. If you want me to repeat the example, come to my office hour, right? Yes. Oh, you're fine. Good. Okay, let's say goodbye to composite. But you will see it right away again in a different context. Okay, visitor. I consider this guy as one of the most interesting pattern for the course. Usually students like it a lot. I actually got maybe a few students telling me that when they actually had an interview around this time of the course, they got asked about visitor pattern. So you maybe pay more attention to this pattern here. It's not easy. It's actually quite counterintuitive, but it's actually very useful. Okay, let's look at the motivating problem. And this would be quite relevant to your projects, I believe, maybe. Okay, let's see a problem here. Let's say we want to have a different problem, no equipments anymore. Let's say we want to design structure for some language. For those of you who took 2001, I believe all of you took it, right? 2001, you learned about context-free grammar. Okay? Now, a little bit similar to that. Let's say we want to support a small expression language where we support integer constants like a 341, integer constant like a 2, And then we also support composite language operation, like a plus, right? Addition. And we can support subtraction, we can support modulo, we can support multiplication, we can support many other things, right? I'll just give you some example here. Okay, so now I'm going to assume, based on what you have learned, of course you're going to review it, about the composite pattern, you can reasonably easily come up with a pattern like this, right? Basically, what we have is, we got expression over here, and then we got constant, which is basic. We also got addition, which is composite, right? Recursive. Now, I'm just making it a little bit easier for me to fit in. Of course, the composite, there should be another one called composite expression, which inherits from composite. Let's just forget about that for now, okay? That would be ideal. Okay? Make sure you're okay with this diagram. We're going to start with this and build it up. Okay, we got expression, we got composite expression, and for the composite expression, we assume we got binary composite expression. We got left and we got right. Okay? Any questions until now? Oh, yeah, sorry, I didn't realize I was blocking you. Okay. Oh, by the way, according to this particular architecture here, how do you create programmatically the expression 341 plus 2? How many objects should you create? Jordan, enlighten us. How many objects? So let me huh? Oh, actually, well, according to this particular architecture, you got either constants or addition, right? These are the only effective classes with plus. So now, how many objects do I need to create in order to represent 341 plus 2? 3, right? You create a constant object for 341. You create another constant object for 2. You create another object with type addition and add those two constants as children. Okay? I rely on you to do it. Okay, this is quite easy. Let me tell you the new problem we have, which is interesting. The problem we have is this. Let's say, for this particular expression here, we assume, for simplicity, let's say we only support constant and addition. Let's just say only that, only those two classes. We can extend it later. What I want to support are operations such as, given a composite tree, I may want to evaluate the expression, for example, for the let me just go to the iPad. That might be easier for you to see. Okay, let's have a look. So that's the composite structure you have over here. Let's say, for example, if you have, let me draw it very quickly, and then I can ask you a question. Let's say we have, let's say, expression over here of type addition, which has left and right. And then the left is pointing to some integer constants. And the right is also pointing to some integer constant. And then we talk about 341 plus 2. Okay? So the first one is going to be 341, and the value for the second one is 2. Okay? So now I want to be able to say, given E, the root of this simple expression tree, I may want to evaluate. What does evaluate mean? Well, evaluate that, right? Evaluate should really give me 343. I did it correctly, right? Sorry, just lost my mind. Yeah, sorry. That's a dumb question. What about print prefix? Well, in this case, it will just give me, basically, it's like a pre-order traversal, okay? If I say print prefix, it's going to give me plus, and then 341, and then 2. Okay? What about print postfix? You're going to print the children first, and then the parents. So it's going to be 341, 2, and then plus. What about type check? Well, type check, for those of you who took 2022 with me since many years ago until now, and also 2030, I always mention about the importance of type. Every time you're trying to apply some operation, it's really important to look at what's the types. Are they being manipulated consistently? So now, if I tell you that I'm doing 341 plus 2, should this be type correct? Well, think about the following. Okay, if you got the intuition it's type correct, that's good. Because we talk about addition. So both sides should be numbers. They are. So that's type correct. On the other hand, if you got something like this, 341 plus true, that's not type correct, right? Okay, good. So that one should be true. So these are 1, 2, 3, and 4. 4 different operations I want to implement for my expression language. And notice that it might be extended for this structure here. We might support all the operators you have in IFA or in Java. We might. Right? So this is just something simple to start with. Okay, without you actually thinking about how to implement those operations which you will do in the projects later. Okay? But now I want you to think about where would you put them? Let me be more precise. I have evaluates, I have prefix printing, postfix printing. Also, I got type check. I got 4 different operations. Where should I put them? I heard expression. That's exactly the answer I want. Exactly. Good. But we're going to see why that design is actually quite not good. Not good. Okay. What you're suggesting is, what we will do is we'll simply put evaluates over here. And then we got print prefix. Also, we got print postfix. And also, we got type check. And we might choose to make them deferred, because at this level here, we simply don't know how to print that expression in general. And then we only make those effective. You know what? Let me see if this might work. So that will make the diagram much nicer. Let me see if I can do that. Sorry, just bear with me. What I will do is I'll erase this part here. Okay, it's really important to understand why this first attempt is actually not good. Okay, one idea would be, I'll put it here. Okay, just imagine they are in this particular box. Okay, just wipe it down. Okay, that's one option here where we simply put deferred for every one of them, just deferred. Okay, and then we put one version over here in the constant. Okay, let me wipe it out over here. Because there's one version over there, I'm going to say that's effective. So I'll say plus, 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 and plus. Also for addition, it might involve certain recursion that you have to write. In that case, I'll put a different color for effective. Okay, how about I say green? Plus, 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 and plus. Okay, make it clean. Because some of you complain in your midterm survey, sometimes iPad gets too messy. I'm trying to do my best. Okay, okay, now, that's the design you just proposed. Why is it bad? Duplicates? You know what? Not necessarily duplicates, I would say. Okay, every time I ask you why is design bad, don't tell me the design smells always. Right? It might smell, but not always, right? For this particular case, there will be no duplication actually, because if you think about how you evaluate a constant will be quite different from how you evaluate an addition. Quite different. So I would say duplication is not a problem. So single choice principle is okay, as far as that is concerned. How about I give you a little bit hint, okay? Rather than telling you the answer directly. Remember singleton pattern? Remember? Yes? Yeah? Do you know what singleton pattern is? Oh, you got to review, right? I'll make sure I put on an exam. I'll make sure. Yeah. All right. Remember back in the singleton pattern, the motivating problem we had. We have a class called bank data. Remember? Oh, sorry. It's a little bit. Sorry about that. Okay, it's bank data. And then we want to have, let's say, interest rates, and also we got exchange rate, etc., right? And then we want to make sure we can support a single instance throughout the runtime of the system, right? One way to do it is simply by basically just put the data access kind of routine in the same class. However, we said that it's a backed design. Because what? There was a keyword that we mentioned. Cohesion, very good. I'm glad. Cohesion. Cohesion. What's cohesion? Anyone from this side? What's cohesion? Anybody? No one? Yeah, true. We're gonna separate. Okay, cohesion. Anybody want to say? Yeah, Jordan, please. Oh yeah, that's fine. That's fine. Okay, cohesion. Right? Of course, you don't have to memorize it. You should understand by your heart. So you can just almost like you memorize it. Okay, cohesion simply means for each class only place features, and over here when I say features, they can be attributes, they can be commands, they can be queries. Only place features related to a single purpose. And this is how I remember it. When you took 2031, what's the guiding principle for Unix commands? Aha, do one thing, do it well. Exactly right. That's exactly what cohesion is about. For every class, do one thing and do it well. Don't try to make a Superman class by mixing so many things. Okay, good. Thank you. In the case of singleton pattern, we don't want to put the data and data access, two purposes, into a single class. So now, if we go back to this particular guy here, now we can have a better ground to judge why this design is bad. Because if you think about it, let's say evaluate. Evaluates versus, let's say, type check. Do they have anything to do with each other? Not quite. One is about evaluate, get some value. Type check is like to say whether it makes sense statically, right? And not to mention, also, if you think about other two, pretty print, right? They also have nothing to do with each other. So now you're putting four operations with different purposes into the same class. That violates cohesion. Okay? That's the second time we talk about cohesion. Okay? This violates cohesion. Okay? Any question about this? So the follow-up question would be, if this design is bad, how do we resolve it? What we really want to have is, we may just want to have a separate place to somehow put each individual operation, somehow. That's where the visitor pattern comes in. Okay? Let's go over a little bit slides, and then we'll see what the visitor pattern is. Okay? Hopefully, at least we can go over the architecture and do the tracing next time. We'll see how much we can do. Okay, this guy here, that violates the cohesion principle, as we mentioned. Okay, cohesion. Okay, and also sometimes people saying you're polluting. Okay, you can see the word I'm using. You're polluting your class by the various different operations. Okay, exactly what we said. Okay, before I talk about the visitor pattern, there's another design principle you have to know. Okay, it's called open-close principle. It sounds contradictory. You got open, you got close. It's not quite. Okay, basically, you remember information hiding that we talked about? Okay, let me just draw a diagram to show you conceptually what that really means. And then we talk about the principle itself. When I talk about information hiding, when we introduce iterator pattern, we say that, imagine that this is your system, your software units that's being developed, right? We mentioned that there is certain parts over there that should be public, right? The green one, that should be public. On the other hand, the orange part, let's say, should be private. Okay, the green part is public. So that means they should be stable. Every time you change anything that's part of your public interface, that's going to affect all the existing clients. Okay. On the other hand, this guy over here should be private. Okay, and then they may not be stable. I'll say may not. Doesn't really mean they should be unstable. They do not have to be stable. May not be stable. Okay, so that's what we said previously about information hiding. Let's go a little bit further. Since I talk about stable, so stable simply means this part of your system should be closed for changes. So which means once you publish your interface, you should make them very stable. That means they should be closed for any changes. They should be. Otherwise, you might have some trouble. Well, I'll show you at the end of the lecture. Okay? On the other hand, when you think about the private part, they should be rather open for changes. You can easily say now, in order for me to implement a heap structure, rather than having array, I'm going to have maybe like a tree structure, right? Linked tree. So if I change that in the open part of the system, which is private, I should feel free to do it because it's not going to affect any existing clients. Okay? Guys, any questions? Somehow I put the two principles together, right? The left-hand side, public versus private, is more like information hiding. The right-hand side about stability of the your system. One part should be closed for any changes. The other part should be open for changes. That's the open-close principle. Okay, let's go over a little bit slides, and then we will talk about different alternatives for us. Okay, so now should be open for extension, some parts, okay, and also closed for modification, right? That's open and close, okay? When extending it, you know what? I would suggest, let me go over this small paragraph maybe at the end of the lecture. So it may not make much sense since we don't have any example just yet. Let me skip that part just for now, okay? I'll come back here. Let me give you some example right away. Let's consider the small expression language that we have. So now we got two alternatives for us, okay? Which part should be open and which part should be closed, okay? That's something we want to discuss, okay? You can see the slides, but I'm going to switch the iPad. I think it's more effective over here. Okay, so now I want you to think about the following, okay? So this is the structure we assume for now, okay? So that's the structure. That's one part of the system. And then, so these are the operations, evaluate, prefix, postfix, and type check. There are 4 operations. So these are the operations part. We got blue, we got orange. We got 2 parts of the system. So now, what are the possible, so open-close principle tells you, for you as a developer, you really should decide which part of the system to be open and which part should be closed. And once you decide, commit to it. You shouldn't change on the halfway through. Okay? Is it correct? I still got more than 10 minutes? Okay, I just want to make sure, yeah. I thought my watch is stopping, right? I want to make sure, yeah. Okay, so now, for this particular expression language over here, I want you to think about the following, right? That will help you design. So I want you to look at this table over here. So we got structure, we got operations. So these are the 2 parts of the system. So now we may choose to make either one of them open and the other one closed, right? Alternative number 1, what does it really mean? Alternative number 1 simply means we're going to make the structure open, and then we're going to make the operations closed. Based on what you have heard me about saying open and closed so far, what does it really mean? When I say somehow I decide to make the structure part of this of the language open, but I'm going to make the operations part closed. What does that really mean? Which part am I trying to make stable? Operations. Good, I agree with you. So first of all, okay, and then I want you to give me a little bit more concrete things specific to this example, but I will help you with that. That's good. First of all, we know that it is closed because we want to make sure it is stable. No change. For example, we don't simply want to change from print prefix to prefix printing, right? For example, right? We don't want to change the name so easily. Okay, so let me give you some example over here, which is more specific to visitor pattern. For this particular alternative, what I'm trying to say is, when I say the structure over here is open, that means it may be unstable. I can feel free to add any new language components to it. For example, I might simply get a new class over here. Oh, maybe not here. Let me say this. So this guy is integer constant, let's say. Okay. And then I might just add a new class over here, call that Boolean constant. And then I can add another class over here and call that maybe multiplication. And then that one there is also going to inherit from the two classes. Okay? I'm talking about alternative number one. So by making the structure unstable and open, I'm saying that I can feel free to actually add different classes to the hierarchy over here. At the same time, this particular set of 4 operations should be kept stable. Should not add any operations to it. Okay, that's what it means. Make sense so far? Okay. Can anybody just try to apply similar logic? How would you explain the second alternative? What does that mean? Let's try.
So your structure is going to be stable, so you're not changing the diagram at all.
Yeah.
You might change the implementation of kind
The operations you meant.
operations.
Yes. Okay. Okay. Let me go over very quickly. For alternative number 2, over here, I'm saying that. So now the operation itself is now open. That means I can feel free to add any new operations to my expression language. For example, I might say now I want to support maybe generate Java code. Okay, that's a new operation. So that means it's not exactly stable. You're just publishing more, like a larger interface. Okay. On the other hand, the structure is now closed. That means you should always just handle these classes only without having any new addition to the classes. Okay. Alternative 1 versus number 2. Question for you. Which one is correct? 1 or 2? Say it again. It depends. Exactly. That's the answer. If you say 1, wrong. If you say 2, wrong. It depends. Depends on what?
Depends on what kind of client with relation with the client.
Yeah, exactly. So it depends on what the client wants. Okay, that's exactly true. Okay. So now, for the visitor pattern, so this is a good starting point about the visitor pattern. Whenever you want to apply the design pattern, you should kind of know what's the precondition or like a prerequisite in order to use the design pattern. For the visitor pattern, okay, I'll write it down for you explicitly. For visitor pattern, if somehow for the particular system you're developing, if you decide the following, if you decide that your system is more like alternative number 2 over here, which means the structure is closed and the operation is open, that is a good candidate for visitor. But if somehow your system is supposed to be alternative 2, it's actually alternative 1. That's not a good candidate for visitor pattern. Okay? I'll write it down. Alternative number 2 tells you that it's a good candidate for visitor. Now, of course, we're going to talk about visitor. So to really convince you later, we're going to show you that once we show you the details about the visitor pattern, we're going to review this expression language over here to say, what if it's actually alternative number 1 rather than 2? What principle are we going to violate? Okay, let me summarize again. In this table here, if you didn't know what to really apply, either go for alternative number 1 or number 2. It doesn't matter. There's no right or wrong. It depends on what you need. However, if you really want to apply the visitor pattern, it must be the case that alternative number 2 is the case. Otherwise, you're not using the pattern correctly because you will violate certain design principle, specifically single choice principle. Okay, we'll see that later. Okay, is it correct? I got 5 minutes. Okay, good. What I want to do now is to go over with you the architecture for the visitor. And then, so that next week, I can finish the tracing of the code for visitor in about 10 or 15 minutes. And then we can move on to other things. Okay? Yeah, let's do that. This is the visitor pattern architecture. 2 clusters. Okay? So you cannot just talk about the visitor alone without the composite. Somehow visitor is a very natural extension to the composite. So you want to talk about two at the same time. Okay? What I will do is I will go over the architecture diagram with you so you can look at that over the weekend. Oh, not the weekend. Today is Tuesday, right? Oh, sorry about that. No. Over Wednesday. Yeah, and then we'll talk about it on Thursday again. Sorry, I thought today is Thursday. Yeah, for some reason. So now I'm going to show you how the architecture diagram looks like, and then I'm going to show you how you can use it. And then we'll explain the details next time on Thursday. Okay? Okay, so now, can you just for now, don't worry about this part just yet. Okay? Focus on the diagram. And to really make you focus. Okay? So now there's no way you can look at the other parts. Remember this expression language cluster? That's composite. We got expression here, we got basic, we got composite, right? The only thing we introduce now is something called accept. That's really important, accept. What does accept intuitively mean? That means for any expression I'm talking about, I'm going to accept certain kind of visitor. The visitor might be for evaluation, the visitor might be for type checking, the visitor might be for pretty printing, right? So now that's why the static type is simply just visitor. So any descendant classes of the visitor can be passed dynamically. And it is deferred, meaning that every effective class over here is going to make that feature effective. Okay, so far so good? I haven't talked about the visitor just yet. I will. And one thing to note, okay? So now, when we draw the client-supplier relation, remember, if, for example, the feature parameter type is of certain class, that is the client or the supplier? Supplier, right? Because we are using the service from visitor somehow. So that is why you will see this particular client-supplier relation, this arrow here goes all the way to the right-hand side of the hierarchy for visitor. Are you okay with this transition here? Okay. We introduce this accept, which is going to make use of visitor, which we're going to talk about now. And this particular client-supply relation is really important. Okay. So now let's have a look at visitor. That's new. Somehow the visitor pattern over here has a very interesting structure. Basically, however your composite structure looks like determines how your visitor structure should look like, somehow. I'll explain to you why. There's an inheritance hierarchy over here. So now we'll see, first of all, you have visitor here, which is deferred. And now, if you look at the features over here, visit constant and visit addition, do you see any rules over here? Do you think the number of features for visit we define somehow correspond to what on the left-hand side in the cluster? Do you see that? I'll give you a little bit of hints. Constant here, constant here. Addition here, addition here. Do you see that? How many effective expression classes you have on the left-hand side in the composite determines how many visit features you want to have in the visitor class, number one. Okay? And then, okay, let me write it down. Number of
So we're effectively turning a type 2 situation into a type 1 visitor pattern.
What do you mean type 2 to type 1?
Like we're taking a situation where the structure is open and the
Open for the operation.
yeah.
Mm-hmm. Exactly. You know what? Maybe hold your remark for now. Maybe it will be more sensible to make that remark maybe at the end. Maybe not today, maybe on Thursday if you don't mind. Okay, please do mention that on Thursday. Okay, give me about 3 minutes. I'll finish that. Okay, it's really important to finish the whole story. So the number of visit features corresponds to the number of effective classes. Okay, I'll put it here. Effective classes in composite. In this case, we got constant, we got addition. So here we got constant, we got addition. Okay, that's number one. Number two, can you see the number of descending classes over here for visitor correspond to what? Operations, exactly. Because we wanted to, let's say we wanted to support 3 operations. That means we need 3 descendant classes. Okay, let me write it down. And then highlight one more thing, and then we're done. Okay, the number of subclasses. Typically subclasses, just directly immediately below subclasses. Number of subclasses of visitor depends on the number of operations you want to support. So that means later on, if you want to support a new operations, which part should you touch? This part. Just add a new subclass, right? And notice that one thing. Since we say visit constant over here, okay, let me highlight it. You can see for the same visit constant class that is deferred at the top level, you have to make it effective version 1, make it effective version 2, make it effective version 3, depending upon what's the purpose for that particular context. It can be, I want to visit the constant for evaluation. I want to visit the constant for pre-printing or type checking. Guys, any questions? That's the architecture for the visitor. Yes, question. Yes, visitor is the supply for the expression. As you can see, the client supply arrow prints this way. Yeah. How does it call visitor? We'll see on Thursday, but not just yet, not yet. Okay, I'll take questions. Yes.
What if the number of operations are, so what if one subclass of the composite has more operations than the other? Does that mean it's not defined?
Yeah, so, okay, good question. You're saying maybe some operations only specific to certain component in the composite. I would say in general, it's not a general pattern, what the general pattern will cover. I would say that like a special case that you got to handle. Okay, but in general, whatever operation you define in the visitor pattern, they should be applicable to every feature, every subclass in the composite. Ah, that's good. That's good. What Uma just pointed out was this. We know that, number one, okay, let me say this, and then we are done for today. Okay, let me say that, very, very important. Number one, if you look at this particular part, you can see visitor over here tells you the visitor is the supplier. Okay? On the other hand, you can see visit constant here takes, oh, let me say that at the top level, that's easier. Visit constant here, we say constant. So now the constant itself is also the supplier. So that means for the visitor, it's both the clients and the supplier. That's the counterintuitive part for the visitor. Because at the runtime, we got something called a callback. That's something we'll see on Thursday. Okay, guys, review this the architecture diagram over here, and then we'll continue from this on Thursday. Okay.